case of the transformer must be grounded according to applicable electrical codes and standards. Use a proper grounding electrode, such as a ground rod or ground bonding plate. When the transformer has no neutral exo tap, the secondary system should be grounded using one of the following methods. Firstly, grounded Y secondary. Install a grounded Y secondary distribution system. Connect the neutral point of the Y secondary to a suitable grounding electrode. Secondly, zigzag grounding transformer. Install a zigzag grounding transformer between the secondary of the delta-delta transformer and the grounded Y secondary distribution system. The zigzag transformer provides a neutral reference point for the grounded Y secondary. Thirdly, impedance grounding. Install a resistor or reactor between the secondary neutral point and the grounding electrode. The impedance limits the fault current and provides a path for ground fault current to flow. It is important to note that leaving the secondary float with no ground reference is not acceptable and can create safety hazards. A proper grounding system is essential for the safe operation of the electrical equipment. Use proper size and type of grounding conductors according to applicable codes. Ensure that all grounding connections are tight and secure. Verify that the grounding system is tested and maintained regularly to ensure its integrity. Consulting with a qualified electrician or electrical engineer is recommended for proper grounding design and installation. Grounding is a critical aspect of electrical safety and equipment protection. In the context of a 240 delta to 480 delta step-up transformer, especially when it feeds multiple machines in an industrial setting, the proper grounding method is paramount. This discussion will focus on the correct grounding procedures when the delta-delta transformer lacks a neutral exo tap, emphasizing why leaving the secondary floating is not acceptable and exploring alternative grounding techniques. The first step in ensuring safety is to ground the transformer case. The transformer's metallic enclosure must be connected to earth ground. This grounding serves to protect personnel from electrical shock in the event of a fault within the transformer. Should a winding insulation fail and come into contact with the case, the grounding provides a low impedance path for fault current to flow back to the source, tripping a circuit breaker or fuse and de-energizing the transformer. The grounding conductor must be sized according to applicable electrical codes, such as the National Electrical Code, specifically Table 250.122. The grounding electrode can be a ground rod, a ground plate, or connection to a building's grounding electrode system. Proper installation involves ensuring that all connections are tight, corrosion-resistant, and meet the requirements of local electrical codes. With a delta-delta transformer lacking a neutral exo tap, grounding the secondary system requires alternative methods. The absence of a neutral point means that a direct ground reference is not available, necessitating the creation of one. Here are three common methods. Firstly, the grounded Y secondary involves converting the delta secondary to a Y configuration and then grounding the neutral point. This can be achieved through a separate Y delta transformer or by rewinding the existing delta secondary. The Y configuration provides a natural neutral point that can be connected to a grounding electrode. The grounded Y system offers several advantages, including voltage stability and the ability to supply single-phase loads if needed. The grounding electrode conductor must be sized according to electrical codes, and the grounding electrode should be selected based on soil conditions and local requirements. Secondly, a zigzag grounding transformer is specifically designed to create a neutral point in an ungrounded delta system. This transformer has a unique winding configuration that allows it to provide a low impedance path for ground fault currents while not affecting normal three-phase currents. The zigzag transformer is connected to the delta secondary of the main transformer, and its neutral point is then connected to a grounding electrode. During a ground fault, the zigzag transformer allows current to flow back to the source, tripping protective devices. The zigzag transformer must be sized appropriately for the system, considering the available fault current and the voltage of the system. Thirdly, impedance grounding involves inserting a resistor or reactor between the secondary neutral point and the grounding electrode. This method is used to limit the ground fault current to a predetermined level. By limiting the fault current, the impedance grounding reduces the stress on equipment and minimizes the risk of arc flash hazards. The impedance can be a resistor or a reactor, each with its own advantages and disadvantages. Resistors provide a stable impedance regardless of frequency, while reactors can provide a higher impedance at the fundamental frequency but lower impedance at higher frequencies. The value of the impedance must be carefully selected based on the system parameters and the desired fault current level. Leaving the secondary floating without a ground reference is a dangerous practice. In an ungrounded system, the voltage to ground on each phase can fluctuate significantly. During a ground fault, the voltage on the unfaulted phases can rise to the line-to-line voltage, which is approximately 1.732 times the normal line-to-neutral voltage. This overvoltage can stress insulation and lead to equipment failure. Additionally, an ungrounded system can make it difficult to detect ground faults. Without a ground reference, the fault current may be too low to trip protective devices, allowing the fault to persist and potentially escalate into a more serious hazard. Furthermore, static electricity can accumulate on ungrounded equipment, leading to electrostatic discharge and potential ignition of flammable materials. Therefore, a proper grounding system is essential for the safe operation of electrical equipment. Grounding conductors must be sized according to applicable codes to handle the maximum fault current that can flow. The size of the grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. The grounding conductor must be made of copper or another approved material and must be installed in a manner that provides a low impedance path for fault current. All grounding connections must be tight and secure to ensure a reliable electrical connection. Loose connections can create resistance, which can impede the flow of fault current and reduce the effectiveness of the grounding system. Connections should be made using approved connectors and should be protected from corrosion. Regular testing and maintenance are crucial for ensuring the integrity of the grounding system. Grounding connections should be inspected periodically for tightness and corrosion. The resistance of the grounding system should be measured to verify that it meets the requirements of applicable codes. Any deficiencies should be corrected promptly to maintain the safety and reliability of the electrical system. Due to the complexity and critical nature of grounding systems, consulting with a qualified electrician or electrical engineer is recommended for proper grounding design and installation. A qualified professional can assess the specific requirements of the system and ensure that the grounding system is designed and installed in accordance with applicable codes and standards. They can also provide guidance on the selection of appropriate grounding equipment and the implementation of proper testing and maintenance procedures. In conclusion, grounding a 240 delta to 480 delta transformer without a neutral XO tap requires careful consideration of alternative grounding methods. The grounded Y secondary, zigzag grounding transformer, and impedance grounding are all viable options, each with its own advantages and disadvantages. Leaving the secondary floating is not acceptable due to the safety hazards it creates. Proper grounding ensures personnel safety, equipment protection, and compliance with electrical codes. It is imperative to use properly sized grounding conductors, ensure tight and secure connections, and regularly test and maintain the grounding system. Consulting with a qualified professional is highly recommended to ensure that the grounding system is designed and installed correctly. The grounded Y secondary method is a common approach when dealing with delta-delta transformers that lack a neutral XO tap and require grounding for safety and operational reasons. This method involves creating a grounded Y configuration on the secondary side of the transformer to establish a neutral point that can be connected to the earth ground. Here is a detailed explanation of how it works. Firstly, transformer configuration. The existing delta-delta transformer does not have a neutral connection on either the primary or secondary side. To implement the grounded Y secondary method, an additional transformer is often used to convert the delta secondary to a Y configuration. Alternatively, the existing transformer can be rewound, but this is a more complex and costly process. Secondly, creating the Y configuration. A Y-star configuration consists of 3 windings connected in a Y shape, with a common neutral point at the center. This neutral point is the key to grounding the system. The 3 phases A, B, and C are connected to the 3 terminals of the Y winding, and the neutral point is connected to the earth ground. Thirdly, grounding the neutral points. The neutral point of the Y secondary is connected to a grounding electrode system. This system typically consists of one or more ground rods, ground plates, or connections to a building's grounding electrode system. The grounding electrode must have a low impedance to ensure that fault currents can flow back to the source, tripping protective devices. Fourthly, grounding electrode conductor. The connection between the neutral point and the grounding electrode is made using a grounding electrode conductor. The size of this conductor must be selected according to applicable electrical codes, such as the National Electrical Code, specifically Table 250.66. The grounding electrode conductor must be sized to handle the maximum fault current that can flow in the system. Fifthly, overcurrent protection. Proper overcurrent protection is essential to protect the transformer and the connected equipment. Circuit breakers or fuses must be installed on the primary and secondary sides of the transformer to interrupt fault currents and prevent damage. The overcurrent protection devices must be coordinated to ensure that the correct device trips in the event of a fault. Sixthly, advantages of grounded Y secondary. Stability. The grounded Y system provides voltage stability by maintaining a consistent voltage to ground on each phase. This is particularly important for sensitive electronic equipment that can be affected by voltage fluctuations. Single-phase loads. The grounded Y system allows for the supply of single-phase loads by connecting them between one of the phase conductors and the neutral conductor. This is a common requirement in industrial settings where single-phase equipment is used. Fault current control. The grounded Y system provides a low impedance path for ground fault currents, allowing protective devices to quickly detect and interrupt faults. This minimizes the risk of equipment damage and electrical shock. Seventhly, considerations. Transformer selection. If an additional transformer is used to create the Y configuration, it must be properly sized to handle the load. The transformer must also be designed to withstand the voltage and current stresses of the system. Grounding electrode system. The grounding electrode system must be properly designed and installed to ensure a low impedance connection to earth ground. The grounding electrode system must comply with applicable electrical codes and standards. Overcurrent protection coordination. The overcurrent protection devices must be coordinated to ensure that the correct device trips in the event of a fault. This requires careful selection and setting of the protective devices. Maintenance and testing. The grounding system must be regularly inspected and tested to ensure its integrity. Grounding connections must be checked for tightness and corrosion, and the resistance of the grounding system must be measured. Eighthly, compliance with electrical codes. The grounded Y secondary method must comply with applicable electrical codes, such as the National Electrical Code in the United States. The NEC provides detailed requirements for grounding, bonding, and overcurrent protection. The zigzag grounding transformer is a specialized transformer designed to provide a ground reference for ungrounded three-phase systems, such as delta-connected systems. It is particularly useful in situations where a neutral point is needed but is not naturally available in the system. Here's a detailed explanation of how zigzag grounding transformers work. Firstly, configuration of zigzag transformer. The zigzag transformer has a unique winding configuration that distinguishes it from other types of transformers. Each of the three phases consists of two identical windings connected in series. One winding of each phase is connected in a zigzag pattern, hence the name. The zigzag connection creates a neutral point that is not present in the original delta system. Secondly, operation during normal conditions. Under normal balance conditions, the magnetic flux is produced by the current in each winding of the zigzag transformer cancel each other out. As a result, the impedance of the transformer is very high, and the transformer draws only a small amount of magnetizing current. This means that the zigzag transformer does not significantly affect the normal operation of the three-phase system. Thirdly, operation during ground faults. During a ground fault, the conditions change dramatically. The fault current flows from the faulted phase to ground, and then back to the source through the zigzag transformer. The zigzag transformer provides a low impedance path for the ground fault current to flow. This allows protective devices, such as circuit breakers or fuses, to quickly detect and interrupt the fault. Fourthly, low impedance to zero sequence currents. The zigzag transformer has a low impedance to zero sequence currents, which are currents that flow in the same direction in all three phases. Ground fault currents are primarily zero sequence currents, so the zigzag transformer provides an effective path for these currents to flow. This is in contrast to a delta-connected transformer, which has a high impedance to zero sequence currents and cannot provide a ground reference. Fifthly, high impedance to positive and negative sequence currents. The zigzag transformer has a high impedance to positive and negative sequence currents, which are the currents that flow during normal balance conditions or during phase-to-phase faults. This means that the zigzag transformer does not significantly affect the flow of these currents. Sixthly, grounding the neutral point. The neutral point of the zigzag transformer is connected to a grounding electrode system. This system typically consists of one or more ground rods, ground plates, or connections to a building's grounding electrode system. The grounding electrode must have a low impedance to ensure that fault currents can flow back to the source, tripping protective devices. Seventhly, grounding electrode conductor. The connection between the neutral point and the grounding electrode is made using a grounding electrode conductor. The size of this conductor must be selected according to applicable electrical codes, such as the National Electrical Code, specifically Table 250.66. The grounding electrode conductor must be sized to handle the maximum fault current that can flow in the system. Eighthly, advantages of zigzag grounding transformer. Ground fault protection. The zigzag transformer provides a reliable ground reference for ungrounded systems, allowing for effective ground fault protection. Improved system performance. By providing a ground reference, the zigzag transformer can improve the overall performance of the system by reducing voltage stress on equipment and minimizing the risk of insulation failure. Compliance with electrical codes. The use of a zigzag transformer can help to comply with applicable electrical codes that require grounding of electrical systems. Ninthly, considerations. Transformer sizing. The zigzag transformer must be properly sized to handle the maximum fault current that can flow in the system. The transformer must also be designed to withstand the voltage and current stresses of the system. Grounding electrode system. The grounding electrode system must be properly designed and installed to ensure a low impedance connection to earth ground. The grounding electrode system must comply with applicable electrical codes and standards. Overcurrent protection coordination. The overcurrent protection devices must be coordinated to ensure that the correct device trips in the event of a fault. This requires careful selection and setting of the protective devices. Maintenance and testing. The grounding system must be regularly inspected and tested to ensure its integrity. Grounding connections must be checked for tightness and corrosion, and the resistance of the grounding system must be measured. Tenthly, applications of zigzag grounding transformer. Industrial power systems. Zigzag transformers are commonly used in industrial power systems to provide a ground reference for delta-connected systems. Commercial buildings. Zigzag transformers are also used in commercial buildings to provide a ground reference for ungrounded systems. Data centers. Zigzag transformers are used in data centers to protect sensitive electronic equipment from ground faults. Impedance grounding is a method of grounding electrical systems that involves inserting an impedance, typically a resistor or a reactor, between the neutral point of the system and the earth ground. This method is used to limit the ground fault current to a predetermined level, providing several advantages over solid grounding. Firstly, components of impedance grounding. Resistor. A resistor is a passive electrical component that provides a fixed opposition to the flow of current. In impedance grounding, a resistor is connected between the neutral point of the system and the earth ground. The value of the resistor is selected to limit the ground fault current to a predetermined level. Reactor. A reactor, also known as an inductor, is another passive electrical component that provides opposition to the flow of current. In impedance grounding, a reactor is connected between the neutral point of the system and the earth ground. The reactor provides a higher impedance to high-frequency currents, which can help to reduce transient overvoltages during ground faults. Grounding electrode system. The grounding electrode system is a system of interconnected electrodes that provide a low-impedance connection to earth ground. The grounding electrode system typically consists of one or more ground rods, ground plates, or connections to a building's grounding electrode system. Secondly, operation during ground faults. During a ground fault, the fault current flows from the faulted phase to ground, and then back to the source through the impedance. The impedance limits the magnitude of a fault current, reducing the stress on equipment and minimizing the risk of arc flash hazards. The impedance also helps to reduce transient overvoltages that can occur during ground faults. Thirdly, limiting ground fault current. The primary purpose of impedance grounding is to limit the ground fault current to a predetermined level. The level of fault current is selected based on the specific requirements of the system, taking into account factors such as the size of the equipment, the available fault current, and the desired level of protection. By limiting the fault current, impedance grounding can reduce the risk of equipment damage and arc flash hazards. Fourthly, reducing transient overvoltages. Transient overvoltages can occur during ground faults due to the sudden change in voltage and current. These overvoltages can stress insulation and lead to equipment failure. Impedance grounding helps to reduce transient overvoltages by damping the oscillations that occur during ground faults. Fifthly, improving system performance. Impedance grounding can improve the overall performance of the system by reducing voltage stress on equipment and minimizing the risk of insulation failure. It can also improve the reliability of the system by reducing the likelihood of equipment damage and downtime. Sixthly, advantages of impedance grounding. Reduced equipment stress. Impedance grounding reduces the stress on equipment during ground faults by limiting the magnitude of the fault current. Minimized arc flash hazards. Impedance grounding minimizes the risk of arc flash hazards by reducing the magnitude of the fault current and the duration of the arc. Improved system reliability. Impedance grounding improves the reliability of the system by reducing the likelihood of equipment damage and downtime. Compliance with electrical codes. The use of impedance grounding can help to comply with applicable electrical codes that require grounding of electrical systems. Seventhly, considerations. Impedance value. The value of the impedance must be carefully selected based on the specific requirements of the system. The impedance must be high enough to limit the fault current to a safe level, but low enough to allow protective devices to quickly detect and interrupt faults. Coordination with protective devices. The impedance must be coordinated with the protective devices in the system to ensure that the correct device trips in the event of a fault. Maintenance and testing. The grounding system must be regularly inspected and tested to ensure its integrity. Grounding connections must be checked for tightness and corrosion, and the resistance of the grounding system must be measured. Eighthly, applications of impedance grounding. Industrial power systems. Impedance grounding is commonly used in industrial power systems to protect equipment and minimize the risk of arc flash hazards. Commercial buildings. Impedance grounding is also used in commercial buildings to protect sensitive electronic equipment from ground faults. Data centers. Impedance grounding is used in data centers to protect critical equipment and ensure business continuity.